All right, everybody, welcome back to the last part of chapter 5.5. But remember, we're going to have a separate lesson dealing with word problems for rational equations as well as rational inequalities, which we're going to look at today. So remember what rational inequalities are. It's when you have a rational function and it's not necessarily equal to, it's greater than or less than, or it could be greater than or equal to, or less than or equal to a certain number. So when we solve inequalities, you might remember that answers aren't x is equal to 5 or x is equal to 9. It's going to be a range of numbers. So it's going to be x are all the numbers between, in this case the example is given to us, -3 and positive 6. So that means that numbers that would be included in the span would be all the numbers up to -3 but not including -3 because it's not less than or equal to. So like 2.99999, -2.99999 would be included, as well as a number like 5.99999 would also be included, but not -3 and not 6. Every number in between that. And it says, inequalities of functions ask us to determine when the graph of a function, the y values, are above or below a certain number. We can do this by graphing the function. So in this case, we've graphed this equation over here on the left, and it says, I want to know when all that stuff over there on the left is greater than 0. I want to know when it's above 0. So we can graph, and I graph this one here over on Desmos. I want to know when is this function going to be greater than 0? Well, I know it's equal to 0 everywhere along this line here. So if I had to decide when is it greater than 0, let's say the whole graph in the top left-hand corner is above 0. So I would say everywhere that x is to the left of -3, it would be above 0. Where else would it be above 0? Well, if I zoom in here, it looks like the graph is above 0 from about -2.5 all the way up to about 4. So I would say so over that span. And then finally, the last one, it looks like that entire graph on the top right-hand corner is above 0. So that looks to be about 6. That's where our vertical asymptote would be in this case. So I would say where x is greater than 6. So those would be the spans of answers where our graph would be greater than 0 in this case. So how are we going to do that when we have an equation? That's what we're going to look at down below. All right, so this one says, what if we don't have a graph? We can fill out the following interval chart for the function and then solve for when the function is above the x-axis or above 0. Our intervals are determined by the vertical asymptotes when the denominator is equal to 0 and the x-intercepts when the numerator is equal to 0. The following function has x-intercepts at 2 and -1, and we can tell that from our graph. There's an x-intercept here at 2, x-intercept here at -1. That's what we did last week. We also have a vertical asymptote in this case at +3. So the intervals that we have across the top go from -infinity to +infinity, but they're broken up by -1, 2, and 3, our x-intercepts and our vertical asymptotes. So all we need to do is list our factors down the side and fill in our chart. So remember, we go through our chart and we say, the very far left side, when we have a big negative, what would our result be? Well, all three of these would be negative. When I multiply a negative times a negative times a negative, the result is negative. That means that graph is below the x-axis, so that means that that is not part of our solution. Then we do the next one, choose a number between -1 and 2, so a number like 0. If I chose 0, we'd have those factors would be the sign, or those would be the signs of the factors. And when I multiply, there's two negatives, an even number of negatives, positive. So that's going to be part of my answer, because I want to know when is it greater than 0. So it's positive, so that's going to be greater than 0. Then we choose a number in the next group. So between 2 to 3 is 2.5. We have one negative in there, that's going to result in a negative, so that's not part of my solution. And then we finally have an interval from 3 to infinity, so a large positive would result in positive, 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 which has a positive result. So in this case, our answer, or our function, will be greater than 0 for the ones that have positives. So from the group of -1 to -2. Oops. And 3 to infinity. Notice that these are curvy brackets because it's not greater than or equal to. If it's greater than or equal to, well, -1 and -2 would be included, and you put these square brackets around it, but it's not because it's just greater than. So this is where we get into some trouble. It's what happens when we know our function, if our function is something other than 0. So the first two examples we looked at were greater than 0. What happens if we have another number? We're going to have to rearrange the inequality and solve it like we did the rational equations. However, we do have one problem. So if I look at this question over here, when we dealt with equations, if this was equal to, what we said was, well, let's take this entire bottom and multiply both sides by that denominator so that we can get rid of that fraction. That's okay sometimes. But remember, what happens if we multiply or divide by a negative number? This sign would have to switch. So that's not always a good option when we're dealing with rational inequalities, because sometimes we might just have x on the bottom. That could be positive, that could be negative. So we don't know, do I flip it, do I not flip it? We should stay away from that. So what we're going to do for these ones, unless we're sure that the denominator cannot be a negative value, then we will have to take 2, bring it over to the other side, get common denominators, and solve it that way. So a little bit more work. That's kind of what's written over here on the right of your notes. It says, remember, if you multiply by a negative, you have to switch the sign of the inequality. Therefore, we can only multiply by the lowest common denominator, or whatever number's on the bottom, when we are 100% certain that it can never be negative. So an example of that would be x squared. Well, even if x is a negative number, I know that the term x squared is going to be positive. That's also going to be true for this example here. I know that this denominator can never be negative because x squared, no matter what x is, when I square it, I'm going to have a positive number. And when I add 1 to it, it's also going to be a positive number. So this is the rare case where I would be able to multiply both sides by x squared plus 1 and x squared plus 1. Because those would cancel out on this side, and I could distribute through on the right side. I can only do that because the denominator can never be negative in this case. X squared plus 1 will always be a positive number. So if that's the case, we can follow through. And we know, just like the equations that we dealt with, I can take 2x squared and bring it over to the left side, and I can take 2 and bring it over to the left side. That will leave me with x squared minus 2x squared, because this one came over, plus 4x, it's already there on the left side, minus 1, and I'm going to have to subtract 2 because that number is going to come over. And it's still going to be greater than 0. So we can bring numbers, we can add and subtract from both sides, not having to change the inequalities, just if we multiply or divide by a negative number. We don't want to do that with inequalities because sometimes it could be positive, sometimes it could be negative. So what I'm going to do is solve the rest of the way through, add our like terms together. Now I have a quadratic. I want to know when this quadratic is going to be greater than 0. So we know that when we solve, we're going to have to factor. So I'm going to factor out -1, because that will leave me with a trinomial with the a value being 1, and I can factor it a little bit easier. So I'm going to factor that trinomial. Look for two numbers that multiply for 3 and add for -4, which are -1 and -3. Those multiply for 3 and they add for -4. Now we have this equation here, and I want to know, when is that function on the left side going to be greater than 0? So I'm going to have to make a factor chart in order to solve this. Always going to do that when it's equal to 0. Now I look at what we're left with. When I make my factor chart, I'm going to break it up by my x-intercepts and my vertical asymptotes. So in this case, we only have x-intercepts at 1 and 3. right? 1 would make this bracket 0, 3 would make this bracket 0. So my intervals are going to go from negative infinity to 1, then from 1 to 3, and from 3 to infinity. I'm going to have my factors down the left side. My factors in this case are, well, I have negative 1, I have x minus 1, and we have x minus 3. And we have our results. So let's fill in our factor chart based on what we know. I know that negative 1, no matter what x is, it's always going to be negatives. Let's take big negatives down the left side. So from something from negative infinity to 1 would be like negative 10, for example, result in negative negative, which gives me a negative result. I want to know when this function is greater than 0. That's what it says on our final line here. So that's not going to be part of my answer. Negative infinity to 1 is not in our answer. Now I need numbers between 1 and 3. Pick a number like 2. If I put that into my chart, I'm going to find out we get a positive result. That's what we're looking for, so that's going to be part of my answer. And then I check the last one, 3 to infinity, so choose a big positive. So in this case, there's only one answer to our answer. X is an element of the set from 1 to 3. It's not greater than or equal to, so I'm not going to have square brackets around that 1 and 3, but that's the only one that's included because that's the only time when our graph is greater than 0 in the positive part of our graph. And that's that one. We'll keep going along. You're going to see it's relatively the same. In these cases, we're going to have a little bit more work to do. For example, 3. So in this case, if it was an equality like we saw before, you would look at this and say, I'm just going to cross multiply and go from there. We can't do that in this case. The reason being, we have an x on the bottom. That could be positive, that could be negative. If I multiply both sides by x, I might be multiplying by a positive. I'm also multiplying by a negative because x is the span of all numbers from negative infinity to positive infinity. Same goes with the fraction on the left side. I have 2x plus 3. I'm not sure if that one's going to be positive or not. If x is a number like negative 10, well, that entire denominator is negative. So I couldn't just multiply both sides by 2x plus 3 because that could be a negative number. Can't do that. We only have one option, and that's to bring all the values to one side. So I could take 2 over x and bring it to the left side, which would leave me something like this. When I bring it over, it changes the sign. Now I need to get common denominators now in this case. So what I'm going to have to do is this term over here on the left is going to need an x on the top and the bottom. This fraction over here on the left is going to need 2x plus 3 on the top and bottom. Right, I can do that to a fraction, multiply the top and bottom by the same term because that's like multiplying by 1. So what that's going to leave us with is common denominator. So across the bottom, I'm going to have x times 2x plus 3. Across the top, I'm going to have x times x and x times 1, which is x squared minus x. Then I have minus, so I'm going to show you, I'm going to bring this one down. So it's subtract whatever I get, all these values. So I have to make sure I have that subtraction in there. So what is that subtracting? So this part came from the first one. We're subtracting all these terms that we're going to have. So 2 is going to distribute through, 2 times 2x and 2 times 3. We're going to have 4x plus 6. But because I'm subtracting that binomial, I'm going to have to distribute this negative through. It's going to have to change the sign of both these ones. That's going to be greater than or equal to 0 still. So I'm going to simplify that top. I'm going to distribute the negative through and add any like terms that we have. So when we do that, we have x squared minus x minus 4x minus 6. That's a big step that a lot of people forget. I'm going to add my like terms across the top. I'm going to try to factor them. So I see I have negative x and negative 4x. I have negative 5x. bottom stays the same. And then I can factor across the top because I have a trinomial. Look for two numbers that multiply for -6 and add for -5, which are -6 and +1. That leaves me with x plus 6, x minus 1. Oh, opposite signs because they need to add for -5. And across the top, 2x plus 3. So that's as far as we can take this equation. Nothing's going to cancel out. So I'm going to have to make my interval chart. I'm going to have to make my interval chart from our x-intercepts, the values of x that make the top bottom, and our vertical asymptotes, the value of x that make the bottom 0. And that's where our chart will be broken up between. So let's figure those ones out. Do it down below here. We have x-intercepts at 6 and -1. We have vertical asymptotes from the bottom, so x will be 0. And in the bracket, think of bringing 3 over and dividing by 2, we're going to have -3 over 2. So I have my interval has to be broken up by those numbers. -3 over 2, which is -1.5, -1, 0, and 6. So I'm going to make that my interval chart over here. We're going to have -infinity to -1.5, or 3 over 2. Then I'm going to have from -1.5 to 1, -1. Then I'm going to have from -1 to 0. And then 0 to 6. And 6 to infinity. So multiple areas of my graph here. We're also going to have multiple factors in this case. My factors are going to be all the parts of my equation, x minus 6, x plus 1, x, and 2x plus 3. So I'm going to put those in. So I have all my factors, and what I'm going to do is fill in my factor chart based on those values that we have. So we'll go through, we'll say, what if I have a big negative value? Each of these will all be negative, which results in a positive. What if I have a number between -1.5 and -1, like -0.25? Which will give me a value like 3 negatives and a positive results in a negative. Then a number like between -1 and 0, like -0.5. So if I put that in, that's a positive. 2 negatives cancel out, we get a positive result there. Next, between 0 and 6, so a number like 3 results in a negative. And finally, the last one, a big positive, results in all positives across the board, gives us a positive. So now I have to look at and see, well, which one of these are the right answers? I go back to my question, and I want to know, when are these factors less than or equal to 0? Less than, so negatives. I'm going to include the negatives. And it says less than or equal to. So that's going to include the extreme values. So when I'm writing out my answer, I'm going to say x is part of. I want to know when it's less than. These two intervals are the ones that are negative. So I know that it's got to be in between -1.5 and -1. Square brackets because it's less than or equal to. And the other one is from 0 to 6. And that's our answer. Any values that are in those intervals would result in that equation being true. And that's that for this one. There's a couple of questions that you can try in your textbook, 295. And we got a joke down at the bottom.